Okay, folks, we're going to look at more complicated rate laws now. You've been looking mainly at first order and second order reactions or reaction mechanisms, but there are some IB questions that involve much more complicated systems, and we'll take a look at that now, okay? The first thing is, if we look at this equation here, this is nitrogen monoxide reacting with hydrogen, and you get nitrogen and water as the products, and that's the balanced equation, and you know that's got nothing to do with the rate law. It's simply this stoichiometric balanced equation, okay? Now, experimentally, it's found that this is the rate law. It's a third order overall, and in previous videos, we've looked at the rate law, and we've decided that we know which particles are colliding with which, and which particles are involved in the rate determining step. But this time, we have it's implying three particles, and a trimolecular RDS is statistically very unlikely. Getting three particles to collide at the right orientation and the right energy at the right moment is very unlikely. So we have to invoke some sort of other mechanism that doesn't involve three particles. And one proposal involves three steps. And we're going to see now something that you haven't seen yet. The first step involves a fast reversible step where two molecules of NO, nitrogen monoxide, react and produce this high energy intermediate. And then this high energy intermediate in the second step reacts with the first hydrogen molecule in the slow rate determining step to produce the first product molecule of water and another intermediate, N2O. And then the N2O reacts with the second hydrogen molecule in a fast step to give nitrogen gas, N2, and the second water molecule. Now, you can see I have a fast reversible step there, the very important RDS, the rate determining step there, and finishing off with another fast step. And you can see that although we're going to do this much later in another video, this is the slow step, and it determines the overall rate. And of course, the slow step has the highest activation energy as well, and we'll deal with that in another video. But now you can see that if I was to cross out the intermediate there, and if I was to cross out that intermediate there, I end up with the overall equation. 2NO plus 2H2 gives N2 and 2H2O. And in fact, I'll delete them now, and there you go. You can see the final equation, the balanced equation, 2NO and 2H2 gives 2H2O and N2. Okay, so I've satisfied the stoichiometry. But if I go back now, if I go back to this here, and you know that when you write the final rate law, the final rate law in previous videos, that's had the same rate law as the RDS. In other words, the rate law would be one hydrogen molecule involved and one molecule of N2O2. But this is an intermediate. It's not an actual substance. Okay, so here we have the balanced equation. Here's the rate law, and here's the same thing written out simply as equations. And there's my crossouts, and I end up with the balanced equation. And you can see that, like in previous videos, we've looked at the RDS and we've derived the rate law. And this is the rate law of the RDS. But in previous videos, we've said that's also the rate law for the overall reaction. But this, as I say, is not a substance. You can't isolate that in a bottle. It's simply an intermediate. Now, you could answer this mathematically, and I'll show you in a moment. But actually, in the exams, you can simply say that one N2O2 is produced from two NOs. So this reaction cannot occur until two of those have reacted. So effectively, this thing here, this intermediate here, is really 2NO. And you could just leave it at that. And you can put NO here instead, and to the power of 2, because there are two particles. Okay? But there's another way you can answer it. And that is, here's the rate law again. The first step involved this. It was a fast reversible equilibrium. And here's the definition here. Equilibrium is where the rate of the forward reaction is equal to the rate of the backward reaction. And don't forget, this is an elementary step, so we know who's colliding with who. Now, if the two rates are equal, that means the rate of the forward reaction which is the rate constant of the forward reaction, times NO squared, 2 particles, is going to be equal to the rate of the backward reaction, which is the rate constant for the backward reaction, times 1 particle of N2O. So they are equal. So that means this quantity is equal to that quantity. So I can now write this, okay? Now you can see, you remember in the previous slide there, that this was present in the rate law, and I said that that's not really an isolated substance. It's not a reactant, it's an intermediate, but we can express the concentration of that in terms of this. I think you can see what I'm going to do here. I'm going to rearrange it, okay? So here I go. I've rearranged that equation so I can get the concentration of N2O2 in terms of NO, and there it is there. So you can see that the concentration of this is proportional to the concentration of NO squared, and this here is the constant then, forward rate constant divided by backward rate constant. Okay, so we're saying that the concentration of this is dependent on the concentration of NO squared. So quite simply then, because of this here, we can simply put that in the rate law instead. Okay, now, so the rate law becomes, there's the hydrogen, and now here is the N2O2, but in terms of NO, which is a reactant, and that's what we want there, okay? Now, if we combine all these K's here, we get the rate law is K overall, NO squared, and hydrogen, and therefore it's third order, and we've got what we want. Okay, so we answered it by simply looking at the particles, and we can also answer it mathematically using the idea of rate constants for forward and backward reaction. Okay, now if I can move on here, this is an exam paper, it's an IB exam paper, an exam question, and it's about this very reaction. But be careful, there's more than one possible mechanism. The mechanism I showed you earlier is not the only possibility, and there are other possibilities, which is going to be shown in a moment. So what I'd like you to do is pause this video now, answer those questions, then start the video again to look at part 2 of the question and answer that. Then you can look at the answers which are on the next slide. So pause the video now and answer all the questions, and then you can see the answers on the next slide, okay, which I'm going to show in a moment. Okay, you can check your answers there. You can see the order with respect to hydrogen turns out to be 1, and NO is 2, as we saw on the PowerPoint. And then you're asked to go through all the other steps here. And the mechanism given in the question, if I go back here, the mechanism here is not the same one as I gave you, but it's still feasible. And the reason is because this X thing, whatever that is, this X here, this intermediate, that is involved in the RDS, but that cannot be formed until one NO and one H2 is reacted. Okay? So therefore, the rate law would involve effectively 2 NOs, one in the RDS itself and one in the first fast step, and 1 hydrogen in the first fast step. So you'd get the same rate law in the end, but this time I've invoked a different mechanism. You have to prove that that's true in your answer. Okay, so there we are. There's the answer slide again. Check it and see how you get on. Okay, thank you.